Hi, so I'm going to show you how to control reasonably high power electronic devices like this bulb and this motor from a microcontroller. So normally, if you wanted to control the device like this bulb, you just plug it straight into the power. So I've got 12 volts coming in here, this is ground, and this is 12 volts, and the bulb will light up. But if we want to turn it on and off from a microcontroller, we've got to physically make and unmake that connection somehow. Now, the standard way to do that would be to use something like this. This is a relay module, and these are really cheaply available for just a few dollars on eBay. You've got two relays, and each relay is basically a magnetically operated switch. So you can actually see here it's marked with a switch and the contact that's normally closed and the contact that's normally open. And you can just put stuff into the screw terminals, and then you apply power and ground here, and then you have the inputs which turn the relays on and off. And that's great if you're using a 5 volt microcontroller, but most new microcontrollers are 3.3 volts. So these microcontrollers are the Espruino boards. This is the Wi-Fi board and this is the Pico board. Both of these are 3.3 volt parts, but they're 5 volt tolerant. So you can still connect up 5 volts to them, and you can connect the input straight up. The problem comes when you start trying to run off lower voltages. Maybe you want to run these boards off of a lithium ion cell that's only 3.7 volts. And now there's only 3.7 volts available to drive this relay, which maybe isn't enough. The problem gets even worse when you're using something like this. This is Puck.js, and it's a Bluetooth microcontroller, but it comes with a 3 volt battery, and it isn't 5 volt tolerant at all. So you have to pull this jumper off, and then you have to provide 5 volts to the relay, and then you have to use the 3 volts from that to connect to this. And then you have to provide maybe more volts, maybe 12 volts, like I am, to power the bulb itself. And it all gets really quite complicated. So is there another option? There is, and it's really nice and easy. You could use a standard transistor, but this is a field effect transistor, an FET. Field effect transistors, they're a bit like a normal transistor in that you put a voltage on a pin and it basically turns on the output. But a normal transistor is sort of a current amplifier. You put current on the pin, and depending on the amount of current you put in, it changes the amount of current that comes out. It just amplifies the amount of current that it can put through it. But FETs, they use the amount of voltage rather than the amount of current to control the amount of current that they switch. And that might seem a bit weird, but what it means is that you don't need any resistors or anything to make this work. You can just connect it straight up. And for devices like this that are powered by a watch battery, it means you don't have to worry about powering this because it doesn't really use any current at all. It only cares about the voltage that's on it. So how do you go about using it? Well, these things are wired up like this. You have the gate, which is on pin 1, you have the drain, which is on pin 2 in the middle here, and you have the source, which is on pin 3 at the end. Now, that doesn't necessarily make much sense, but the way you would wire it up is like this. So you have your microcontroller here, and you have the FET here. Now, you actually, instead of the obvious thing, which is how you might usually control the device, which is to switch the positive voltage, you actually leave the device connected to the positive voltage here, and you switch the negative voltage, and that means that the actual voltage that needs to be produced by the microcontroller is really quite small. So basically all we have to do is connect this to ground. We have to connect it to the side of the thing we're driving that used to be connected to ground, and then we have to connect it to power. So if I just do that, so we have the bulb on, which was like this. If I just take this and put it in the breadboard, and if you haven't seen this before, in a breadboard all of the columns are connected together, so it's just a nice easy way to connect things. So what we're doing is we're actually leaving positive connected, and now we're going to connect ground to pin 3, And I'll just bring this back on so you can see what I'm doing. And then we can connect the bulb to pin 2. And you notice it's already come on slightly. And this is because there's so little power needed to make this work that just the voltage that's on the pin at the moment is enough to turn the light on. So if I now add another wire, this would be the wire that went to the microcontroller to here. We can turn it off by connecting that wire to ground. But if I let go of it, just the voltage on my fingers is usually enough to turn the light on a little bit. But okay, it's not. Oh, there you go, just a little bit. But if I touch my hand onto here now, just the resistance of my hand is enough to turn it on much more strongly. And again, I let go and it will just keep running because it's not using any current really. So to connect this to a microcontroller now, all we have to do is connect up the ground wire, which is pin 3. Now obviously, as we did before, we can just short this out to turn the light off. And I've programmed this microcontroller so that pin D1 here is going to be switched on and off whenever a magnetic field is near it. So I put these two in, and now if I just bring a magnet close, we'll see that the light turns on and off. Now we don't have to do that with the light. We can just obviously swap that all over and put a motor on. So motor again, positive goes directly to battery positive, and the actual drive goes to pin 2. And now if I do this, it'll turn on. But with motors and other inductive loads, and things like solenoids, for instance, if you were using a water valve to turn water on and off from one of these devices, then you have kind of a problem with the induction. So what that means is that when you release the voltage, you get a kind of backwards voltage generated by the coil. So what's actually happening is we've got like time here and voltage here. So it's fine normally, and then we turn it on and everything's great. But then when we let go of this, there's nothing to really stop the voltage from moving around. So instead of just going back down to north, it'll do this. And this can be very bad for the FET. Now the FET we have here actually has some protection built into it, but it's not really enough for really big loads, so you'll want to add something else. So that's why you want something like this, which is a diode. This is a 1N4001, and it's like a completely standard diode. You can get loads of things like it. All you really care about doing is making sure that in here, when this is on, it's fine, but when it's off, we want something to stop that voltage going down below that line. So instead, we just put a diode. We just put a diode in here, and this means that that normally the diode won't conduct, but when the voltage is released, it will just clip it and stop it going. So all you have to do is put the diode between pin 2 that we had and straight across here, and you want to make sure you get it the right way, because if you don't, then when this turns on, it will actually try and put all the voltage through the diode and it will make it smoke. So hopefully I've got this right and it's on, and when I take the magnet away, it'll stop working. And that's it. You can easily do this for any other microcontroller. All you have to worry about now is connecting ground and the data pin itself. And you can put even more of these all together, and you can share the same ground and just have one wire coming for each thing they control. The only problem with this is when you want to start turning this motor backwards instead of forwards as well. And for that, you need to look at using something like a motor driver chip. But using these FETs is a fantastic way of driving things, and I will put a link to the exact FET number I used in the description. not every FET will work because the FETs, their current depends on the voltage that goes into them. And older FETs will tend to require a much higher voltage to turn on completely. These FETs require a low enough voltage that even the 3 volts that comes from this watch battery on the back of the Puck will be enough to turn them on completely. If you don't, then your motor will still work, but a lot of the current will be synced in this itself, which will make it very warm, and that's probably not what you want. If you like what I'm doing, please subscribe to me on YouTube, take a look at the Espruino website, and please consider getting one of these Espruino boards or the Puck.js. Thanks for watching.